All right, ladies and gentlemen, class recording has started. So if you feel the need to shout anything inappropriate, please be aware that this will be on the internet for all to see, including your mom. So just think about that. You know. All right. The last section of chapter 4 that we've been dealing with has dealt with motion in 2 dimensions. And we introduced this idea of motion in 2 dimensions through this picture. I mean, this is the first, not that one. This is the first picture that we looked at. I mean, not the only picture, obviously, but we talked about the idea that this girl on the rollerblades, right, we reviewed this yesterday, because she's holding this ball, it's moving horizontally. And at that moment in the picture, she lets it go. And gravity starts affecting it, right? And gravity causes it to go faster in the downward direction and faster in the downward direction. All right, that's not straight. Let's fix that. There we go. Okay. But we said that it maintains that horizontal motion because of that whole independence of motion idea, that what's going on horizontally doesn't affect what's happening vertically, right? And we went through, and we did this at the beginning of class yesterday, right? We talked about the idea that if there's 2 things going on, we need to analyze those 2 motions separately, right? X column, Y column, and we talked about that when we're looking to analyze that motion, we're looking at 6 things. Where does it start on both the x and the y-axis? Where does it end up on both the x and y-axis? What was its initial velocity on the x and y-axis? What does it eventually end up doing on the x and y-axis? What's its acceleration? What's its time? Right? And we talked about the idea that we can fill in these accelerations right away. You know, those accelerations, 0 on the x-axis, negative 9.81. The fact that this time here and this time here have to be the same because the horizontal and the vertical motions occur simultaneously. So however long the time is for one, it's got to be the time for the other one. And then one important thing that we did yesterday was that initial velocity on the vertical axis was 0 because when this object became a projectile, when it came under the influence of gravity, it was traveling horizontally because of the fact that it was being held by this girl as she was moving along. Okay? And we referred to that as a horizontal launch. Okay? And we then basically said, okay, we took it from there and said, okay, where's it going? What's its distance? Blah, 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 blah. Okay? Today, we're going to change that up a little bit. And that starts with this example problem called a rough shot. So it says, chipping from the rough. A golfer sends the ball over a 3-meter high tree that is 14 meters away. And you guys have this problem on your sheet here, so it's kind of small, but hopefully you might be able to read that a little bit better than what's up on the board. Okay. It says the ball lands, on the green of course, at the same level at which it was struck after traveling a horizontal distance of 17.8 meters. So A says, if the ball left the club at an angle of 54 degrees above the horizontal and landed on the green 2.24 seconds later, what was its initial speed? Okay? So, first things first. What is this problem asking us for, at least in part A? Velocity initial. Okay? Now, this gets a little bit trickier. When we did this problem, the only velocity initial that we had to talk about was the horizontal velocity initial, because this object became a projectile when it was already traveling horizontally. But if we look at this picture, right, this ball does not become a projectile when it's traveling horizontally, right? It gets hit up into the air or launched at an angle. So the initial velocity, or the initial speed, if we disregard the direction, or they gave us the direction actually, okay, is actually going to be a combination of the two initial velocities, the horizontal and the vertical. So we actually have two unknowns in this problem, because to get the initial speed, right, we need to know what it was doing horizontally and vertically. The one big change that we make in this problem versus the previous problem is the fact that, where is it? Next one down. That we can launch this projectile at any angle. We don't have to launch it horizontally like that girl holding the ball or while she's on her rollerblades, or the pumpkin that you threw off the edge of the tower yesterday in the problem that you did. Okay? Here, we launch this object at an angle. It becomes a projectile, not while traveling horizontally, but while traveling at some angle in relation to the horizontal axis. When that happens, it actually has two initial velocities. Just like in the problem we did yesterday with the waterfall, we had to find the two final velocities, right? You found the final velocity horizontal, and you found the final velocity vertical, and then you found the resultant of those two, right? Just like this picture here, right? At the end of this, when this object is getting to the end, it's actually traveling both horizontally and vertically, and the actual speed is the resultant of those two, right? The hypotenuse of that triangle. Same idea, except now we're dealing at the beginning of that object's flight, not the end of its flight. Okay? But how we handle this problem is no different than what we did before. X column, Y column. Okay? And then the things we're looking for, right? Where does it start? Initial positions. Where does it end? Final positions. Initial velocity, final velocity, acceleration, time. Okay? Good there for starters. All right. So we've already established the idea that if this problem in part A is asking us for the initial speed, we have to take into account two factors. What was it doing initially on the x-axis, and what was it doing initially on the y-axis? So we actually have two unknowns in this problem here. Okay? Now that we've established what we're looking for, let's start filling in things in this chart that we know. So we said that there were two things that we could fill in right away, regardless of the kind of problem that we're doing, right? What can we fill in right away? The accelerations. Regardless of the fact that we shot this ball up into the air as opposed to throwing it horizontally, that does not change the fact that gravity is acting on it vertically, and nothing is acting on it horizontally. Okay? That does not change. So those accelerations still remain 0 on the x-axis, negative 9.81 on the y-axis. Okay?
Good morning. Please pardon the interruption. If you are a participant in a club or activity and need to set up for the activity fair next period, you may do so at this time at your teacher's discretion. Thank you.
All right. So next, let's start filling in some other things they gave us in the problem. What else did they tell us about the flight of this ball in the problem? Time. Okay, it gave us time, right? It says that it lands on the green 2.24 seconds later. Which time is that? Both, right? Doesn't matter, because the time horizontal and the time vertical have to be the same. Okay? What else did they give us about the flight of this ball?
X final.
Okay? It gave us x final. It says it travels a horizontal distance. Ooh, that's a bad line. It travels a horizontal distance of 17.8 meters. That means it ends 17.8 meters away, as long as what? What do we have to do in order to make that assumption? Where's our reference point in this problem? Okay? This initial spot where the golf ball was starting, that's probably going to be our reference point, right? So that means what was the initial position of this ball? 0, and it ends 17.8. Okay? Now, that being said, we can also use that assumption to get a couple more things on this chart. Right? Where does the golf ball start on the y-axis? Starts at 0 if we make that our origin point. What does it tell you about where the golf ball lands? Okay? It says at the same level at which it was struck. And that means if it started at 0, what does y final have to be? 0. Now remember, that only takes into account the y-axis, up and down. It doesn't, making these both 0 doesn't mean that it ends up in the same place that it started. It means it ends up at the same height that it started from. Okay? So don't get confused there, right? Just because we made these both 0 doesn't mean it ends up in the same place. It ends up at the same height if we assume that ground is level, and we'll go from there. Okay? All right. We talked about that one of the equations that we use a lot in this section here deals with taking and figuring out the position of an accelerating object based on its acceleration, the time, its initial velocity, right? And we said that we can also do that for the y-axis as well, right? Plus v initial t plus y initial, okay? With that much information, do we have enough here in order to find the initial velocity on the x-axis and the initial velocity on the y-axis? Right? Here, there are 5 terms in this equation, right? X final, acceleration, time, v initial, and x initial. Guess what? We know 4 of those. Okay? So using these 2 equations, you should be able to figure out v initial on the x-axis and v initial on the y-axis. Why don't we do that now and find out what those 2 initial velocities are on each axis. All right. How's that? We okay with those two? But is that the answer to this question? No. The answer to this question asked us for the initial speed. We just found out how fast this golf ball was traveling initially on the x-axis and how fast that golf ball was traveling initially on the y-axis. Okay? The initial velocities, horizontal and vertical, but that's not what this question asked us for, right? We said that if it's traveling on those two directions at the same time, the actual speed is the resultant of those two, right? So we know that this is 7.95, and this is 11.0, okay? To find the resultant, what are we going to do here? Pythagorean theorem, right? Make this into a triangle. Second one starts where the first one ends. Does it matter which one's the first and which one's the second? Not really, right? But then the resultant is that hypotenuse of that triangle. Okay? Did we get 13.6? Yeah. Good there. Okay with that? So we see here, right, this problem is not any different than the problem that we've done before, right? Make the list, find out what you got to get, but some of the things that we assumed before, we can't assume anymore. Okay? Lauren, you okay?
Oh, yeah, I figured out what I did.
Okay. Good there? All right, let's tackle part B. Okay. All right, I'm going to take this and start me a new page. Okay. So it says the ball passes directly over the tree at t equals 1.76 seconds. How high was the ball at that time? So, what is this question asking us for? Final Y, right? Where, how high does it end up? So, we're going to start X chart, or X column, Y column. Now, because this is a different problem and a different point in the height or the flight of this ball, right? The chart looks the same, but it's different information, right? V initial, V final, acceleration, time. Okay? If it's asking you how high the ball was at that time, right? It's saying the ball goes up, right, like this, and now it's right here, that point of its flight. And it wants to know, right, how high that ball is at that moment in time, right? It better be taller than what? It better be taller than 14, right? Because that's how tall the tree is. Okay? Oh, wait, sorry. 3 meters high. Sorry. 14 meters away. Okay? All right, so we need to know this, right? What are we looking for on the y-axis? All right, now we start filling in things we know, right? First thing we can fill in?
Acceleration.
Put the accelerations in. This is still 0. This is still negative 9.81. Okay? Now to the specifics of this problem, right? What else did they give us?
Time.
Give us the time, right? 1.76. 1.76, because that's when it passes over the tree. They also gave us,
Final X.
okay, they told us how far away this tree is, right? It's 14 meters away. That's where it is, that's how far horizontally it traveled. if, once again, we assume that this point right here being our reference point. And that means it started at x equals 0 and y equals 0. Now, we also have a bit of information from the previous problem that we can use, right? What did we figure out in the previous problem?
Initial velocity.
The initial velocities, right? The fact that now we're talking about passing over this tree versus when the ball landed over here on the ground, does that change what was happening way back at the beginning? No. So this is going to be 7.95, and this is going to be 11. Okay? Good there? Going back to the equations, right? On the left-hand side, is there anything that we don't know yet that showed up in that original equation that we've been using? Right? We know everything that's in this equation, right? 1/2 at squared plus vit plus x initial, right? There's nothing in that equation we don't know. But we're not worried about that side, right? We're worried about this side, the vertical side. And right now, in that equation, we said there were 5 things. And if you look at our chart, we know 4 of them. So go ahead, solve for y final. Hopefully it's pretty easy. You don't even do any algebra. Just, you don't have to rearrange the equation or anything. Keep your positives and negatives straight, because that does show up in this problem, right? We end up with positive 4.05. Hopefully.
I got 4.6.
Let's do this.
Just around here.
Oh, did you use 11 for your initial velocity, or did you use like 10.98? Okay. I got 4.16. Apparently I don't know how to plug things into my calculator. Just turned off on me.
Oh, wait, just a second.
Yeah.
What do you use for the initial, or, yeah, for the initial velocity, you
So-
don't use 11?
Yeah, you can use 11. Although some
Oh.
people, like on the last problem, some people might have rounded like 10.99 or something like that, because that
Okay.
is like your calculator gave you that.
Yeah.
4.16, is that better? All right, good there? All right, so let's look at this golf ball a little bit more, all right? So we talked about here that we looked at how high it was at that particular point in time, okay? Down in the bottom left, it asks you another thing about that ball, right, it asks you, I'm going to, hold on, do this. I'm going to, no, what am I going to do? I am going to take my picture. Okay. I'm going to take it here and put it on this one. So, number 40, which is on the next page of your book, but down in the bottom left, says, what is the speed of the golf ball when it passes over the tree? We found out the height of the golf ball at that point in time, but now it wants to know what the speed is. Okay. But, just like yesterday, right, if we looked at speed, this golf ball will be doing two things at this point in time, right? What's it going to be doing? It's going to be moving horizontally, right? But it's also going to be doing what? Vertically too. If it's past this top point, what should we see about its vertical velocity at that point in time?
It's negative.
Should be negative, right? So, x, y, right? Initial position, final position, initial velocity, final velocity, acceleration, time. Okay? If we want to know the speed of the golf ball when it passes over the tree, we actually have to know two things in this chart, right? What do we need to know? If we want to know the speed of the golf ball at this point in time when it passes over the tree, we actually have to know two things. What do we need to know? We need to know this, right? And we need to know this. What are the speeds, both horizontally and vertically, at that moment in time? Because then we take those two, right? We take these two arrows and we find the resultant, and that will be the actual speed. But before we find the resultant, we got to know the two individual speeds, the horizontal and vertical. So we start plugging things in that we know. First thing, do the accelerations, right? Those can go in right away. Now, a lot of the things that we did in the last problem still apply. For example, we know that the time was 1.76. We know, way back from the first problem, that the initial velocity was 7.95 on the x-axis and positive 11, sorry, 7.95 on the x-axis, positive 11 on the y-axis, right? Because it initially got shot upward on the y-axis.
You want that on
No, that's not that good. It doesn't go there. It goes here, and it goes here. Sorry about that. But we do know those, right? We know that this is 0, and this is 14, right? And that this is 0, and we just found out that this is positive 4.16, right? Found that out in the last problem, but that's where that ball ended up. Okay? Now, we talked about that when we're dealing with finding speeds, right? V initial t plus y initial, right? This equation doesn't do us any good. Because why?
because it doesn't give us velocity final.
V final isn't in this equation, so we can't use this equation to solve for V final. But, like we said, it's still an accelerating object, so we can still use kinematic equations to solve for the final velocity. Now, before we start plugging numbers in, we can actually figure out one of these before, based on something that we talked about yesterday when you were doing your problems. What's the acceleration on the x-axis? If the acceleration is 0, that means what?
Velocity is final.
That means that the velocity is what?
Constant.
Constant, right? And if the velocity is constant, if we know the initial velocity, guess what the final velocity has to be? The same, right? So we can take this without doing any calculations at all and make this also 7.95. Is it 7.95? 7.59? Okay. Thought it was. I just started doubting myself. But now, right? Now we can take this second equation here, right? And we can start solving for what we need to solve for, right? We need to know V final. Now remember, when we use these equations, we got to make sure that we keep things separate, x-axis, y-axis, right? So, the initial velocity in this case was positive 11 plus the acceleration, negative 9.81, times the time of 1.76. Get that there? Negative 6.27?
Yeah.
But, is that the answer?
No.
Not the final answer, right? We said, at this moment, right, that golf ball is traveling both horizontally and vertically. We know that this is 7.95 at that moment, right? And now we just figured out this was 6.27. Okay? Now, a lot of people ask, when I write this, do I have to write this as negative 6.27? And the answer is, you could, but what did we say the negative tells you? Direction. The negative is just there for direction. Can you tell which way that velocity is going from my picture? If I draw the arrow down, the direction is implied there as well, right? So, make a triangle, right? And the actual speed in this case, right, is the resultant from here to here, right? The hypotenuse of that triangle, okay? And even if you plugged in negative 6.27, when you do Pythagorean theorem, what do you do to that number anyway? You square it, right, it becomes positive, so we don't have to worry about that anyway.
Yeah.
So that will give you the right direction. Good there? Questions? All right. Calendar. What? I know, we're not going to have time to do it though, so we'll do it. All right. So on the calendar, right? These problems dealing with those angle launch and some of the velocities and things that happen at that point in time. Okay? Answers are there. Monday we'll come back and do some problems. Okay?